So the last video ended with this list. We said there's a couple really significant benefits to doing this kind of lower bound analysis. So now very briefly, I want to talk about this last one. How can we use this to identify bottlenecks in algorithms? So to do this, to discuss this, I will begin with a bold claim. Here's my bold claim. There exist linear time sorting algorithms. Okay, so you should be pointing your finger now in disgust, saying, you just told me that the fastest sorting algorithms can never be faster than n log n. And I say, no, I didn't say that. Right? What did I say? I said the fastest comparison-based sorting algorithms run in time n log n. So what that does, when I'm very specific about having said that it's the comparisons that kind of, our entire analysis was hinged on this idea of a comparison basis for the algorithm. What that suggests is that if we can come up with an algorithm that isn't comparison based, then maybe we can go faster. So you might think about it and say, how could you possibly have an algorithm that's not comparison based? Well, one of the classic algorithms that is not for sorting that is not comparison based is called counting sort. And the idea of counting sort is, rather than looking at individual items and comparing them, what we'll do is we'll just count how many of each item we have, and then use that to sort the list in the end. Okay, so how does this work? Well, first let's think a little bit about an application. And so what comparison-based sorting does, the old kind of sorting, the sorting you're used to, is it says, here's an array. And that's all it does. Right? All it does is say, here's an array, now sort it. So in a comparison-based sorting algorithm, all we know is that there's an array and that we have some way of comparing elements in the array, but we know nothing necessarily about what the elements in the array are. In counting sort, you're given an array, but then you're also given, or you're assumed to know, a list of potential items that belong in the array. And this could come in a couple different ways. So for example, we could say these are integers, and you know a lowest integer and a highest integer. So that means that any integer along that in that range might be a valid element of the array. You might also just know that there are a finite number of things, and you might know the identities of the things. So for example, the array that you're being asked to sort could be a table in a database, where the database contains records of people in the United States. Right? There's 300, 320, 330 million people in the United States. And one of the fields in the database might be like the birth year. So there are very few possible birth years for people currently living in the United States. About 120 of them at the most. But there's 300-something million people. So there's very few birth years compared to the number of people, which could be a really good example of how to use counting sort. So suppose you have a situation like that. You know exactly which items might appear in your array, and you know there might be multiple copies of each item. Well, then counting sort might be a good algorithm for you. And there's actually, just as a note, there's also a variant of this that uses the same kind of idea called Radix Sort. A little more general, a little more applicable to things like unsigned integers, big numbers like that. So here's how counting sort works, and I'm just going to illustrate this by working an example. So suppose here's our input array. Our input array is going to be composed of just a small number of possible elements. So it'll just be composed of elements between 0 and 3, right? So just integers from 0 to 3. So it's going to go like this, and I'm just making this up as I go. So 3, 1, 3, 2, 2, 0, 1, 2. Okay. So here's our input array. Right? It's got 1, 2, 3, 4, 5, 6, 7, 8 elements in it. And so here's what we do. And in counting sort, anytime you're doing counting sort, you have to have this knowledge of what numbers can appear in your array. So here is our knowledge of what numbers can appear. So I'm going to write a list of possible elements. So the possible elements are 0, 1, 2, and 3. Okay, so now here's how counting sort works. For each possible element, So what you do is you walk down the input array, and then you increment the count of that element. Okay, so here's our possible elements, here's our counts. So we look here and we say, there's a 3, right? 1, 3. Now there's a 1, so there's 1, 1. There's 2 3s. Now there's a 2. Now there's a second 2. We found a 0. Now we found another 1. And now we found a 2. So this is fast, right? Why is it fast? Well, because I can use this as an index for this array. Really an index for this array. Okay, so the lookup to that counts array is going to be fast, and we just use the identity of the element in our input array as the index for our counts. If the counts, or if the possible elements are something else, then you might have to use some kind of a hash map to index them, which will be slightly slower potentially, but still it's going to be quite a fast operation to go look up the spot in our counts array and increment it. So then once we have our counts array, what do? Well, we just walk down the counts array and start building up a new list. So here's the first spot in our counts array says there is 1 0. So our output will start with a 0. And then our second spot in the counts array says there's 2. So we say, okay, this index gets repeated twice. So 0, 1, 1. And then this index 2 gets repeated 3 times. So 1, 2, 3. And this index gets repeated twice. 3, 3. And we're done. Okay, super simple. So what does this take? Well, it takes one pass down this. One pass. Right, one pass to build up our counts. And then it takes one pass here. Okay, so what's the time complexity of this algorithm? Well, this should be n. And let's just say, for instance, that there are k possible elements. So I'll just write k possible elements. So the one pass here is, so that'll take k steps. So our overall complexity is n plus k. Big data of n plus k. Okay, so if you have a very large input array, but very few possible elements, such as the database of all humans in the United States with their birth years, there's very few birth years compared to people in the United States. So the n would dominate, and you'd get essentially a big theta of n algorithm. If you have many possible elements, then the k might dominate, and the n might be fairly small. So there's a trade-off certainly in terms of like the relationship between n and k that tells you whether or not you should use something like counting sort. But regardless, counting sort is a linear time sorting algorithm. And so this is just one example of how knowing something about the lower bound of an algorithm's complexity, or the complexity of algorithms that solve a particular problem, can give you information about how to do better. Here, what we learned when we did the lower bound analysis for comparison-based sorting is that it really hinges on comparisons. So we said maybe there's faster algorithms, but if they are, they can't use element comparisons. They would have to use something cleverer, like indexing, like simply indexing the count array, like we do in this one. And so that's this is as far as we will go in the course with this. There's plenty of information that you can find on Google or Wikipedia, about counting sort or about its cousin Radix Sort. But in any case, this is one of the big takeaways that you should learn from this lower bound analysis, is that if you do the lower bound analysis, it can help you find bottlenecks, which then help you design better algorithms for variations of the problem. The other thing you should learn is that we didn't get this linear time algorithm for free. We do lose something by saying let's not use comparisons. And in particular, what we lose is to use something like counting sort. We do need more information about what the array is going to look like. And counting sort, the information it uses is the identities of the possible elements. And for other algorithms, there may be other potential gains we can get, but we always have to give something up. comparisons they gave us the nice power to be able to sort totally unstructured arrays that we had no prior information about.